for the invitation. Yeah, so today I'm very excited to share some of our recent work on scaling up repeat training. So yeah, so when we are talking about scaling, like whether it's for language models or for vision models, there are usually some like common strategies of like how to scale up the model. So one is to just using larger models, like adding more and more parameters in the model. For example, for vision, you have VIT base to large to giant. And for language models, you have like 3B, 7B, 13B, or even like larger and larger LLMs. So that's definitely one way and probably the most effective way of scaling up your model, scaling up your pre-training and uh, having like better performance. And another way of scaling is like you can use the same size of model, but you add more and more data in your training. So apparently like more data can like make your model like more robust and more generalizable. Um, and for last one, you can also train the model for like a longer range of time. For example, as long as you have enough amount of compute, you can train the model for 100 epochs, 200 epochs, like or like more and more. And there are lots of uh, research about like how to balance these three dimensions of scaling. Like there's some like scaling laws, like the chinchilla scaling law and some other scaling laws that have lots of discussion on that. And uh, in this talk, I mainly want to talk about the first dimension, which is the model size. So basically, we want to fix the last two dimensions, the data and the training, and we want that like when do we not need larger models? So we want to argue against the model size in this case. So this is a joint work with some of my lab mates at Berkeley and also alumni from at Microsoft Research. Yeah. Okay. So so we talked about like there's the three dimensions of scaling, right? The model size, the data size, and like the training time. But there is actually a fourth dimension of scaling for vision models. So normally we get like larger and larger performance, like better and better performance by using larger and larger models. So this is what we usually do. But the fourth dimension of scaling is we can actually use the same size of model, but we use larger and a larger image size. For example, we can scale up the image size from 256 to 512 to 1024 or even higher. And sometimes we do this too. For example, like there are some models like Dino V2, which use an image size of 518 instead of the regular 224 image size. But not many like pre-trained vision models are using like larger image size. But in this work, we want to show that image size or image scales is actually matters a lot for video pre-training and for performance of your vision model in lots of downstream tasks. And so there are mainly two findings in our paper. So the first one is that we find that larger image scales usually make your model perform better than larger model sizes. So basically, uh, you use the same size of model like VIT base, but you use larger and larger image input, and you can usually get better result from this way than using larger and larger model size like large model or huge model. And what surprises me a bit is this is even true when your model is not pre-trained on any larger images. For example, you can just take a VIT pre-trained on small images, like 224 images. And you can just run this VIT on larger images when you are doing some downstream tasks, and you can still see that this one is performing better than using larger pre-trained model like VIT large or VIT huge. So that's the first finding. And the second one is, so larger image scales, they have better performance, but we also find that they have similar or even larger capacity as larger models. So this means that like a smaller model with larger image can actually learn a similar representation as larger models. And this has some indications, and one of that is you can actually, like when you pre-train your model with larger images, you can actually have even better results. So that's basically like two points in our paper. And let's dive into the first one. By the way, you can feel free to interrupt me if you have any question. Yeah. So before I share with you how we how we run a VIT on larger image, I want to show some results, like some comparison between image scales and model size. So basically, our observation is that using larger image scales is usually better than using larger models on lots of downstream tasks. For example, here we are evaluating on 3 classic computer vision tasks. So the ImageNet classification, the ImageNet classification, semantic segmentation, and depth estimation. And we are evaluating 3 pre-trained models: the ImageNet pre-trained VIT, DynaV2, and OpenClip. And for each of the figure here, there are 2 curves here, and the gray curve is when you are using scaling up the model size. So here, the size of the circle represents the size of your model, and you can see that for this curve, the size of the model is larger and larger, and the compute you are using, which is measured by GFLOPS, is also larger. And the green curve here is keeping the same size of model, so you can see that circle is the same size, but using larger and larger input image. And larger input image will also make your GFLOPS to go higher. So that's the green curve here. And you can find that in lots of cases, like for example, for these 6 cases, the green curve is usually on par with or even better than the gray curve. So this means that starting from a VIT base, you can actually have better results by using larger inputs than using larger model size, like large or huge or even giant models. And for some of these cases, starting from VIT base is probably worse than using larger models, but you can start from VIT large and have better results. And of course, there's one failure case where either starting from base or large cannot compete with larger models. But it seems that in lots of tasks and lots of pre-trained models, using larger input images is actually performing better. And this is not only true for these classic computer vision tasks, but also true for lots of other tasks. For example, lots of benchmarks in multimodal LLM. So basically, what we do here is we take a lava, and we keep the LLM part, and we just change the vision part. So either you can change the size of the vision model, or you can change the size of your input image. And we can see that for different types of benchmarks, using green curve is also better than the gray curve. So which means that larger input images is also better for multimodal LLMs. And especially for detailed understanding, larger images matter a lot. For example, here, it's like, I think it's an image of probably 2K by 3K resolution or something like that. And there's one very tiny object here, which is a red bottle. So this object probably only takes like 20 by 30 pixels in the image. And when you ask the model of like what is color of the water bottle, like regular vision language models will get the wrong answer, but using larger image will get you the right answer here. And we also tried some robotic tasks to get like a holistic evaluation of the vision representation, and we also see that okay, using a larger image is also better here. So yeah, so this is showing just cube stacking task here. And so it seems that like for all these benchmarks and downstream tasks, larger images actually matter a lot. And you might wonder like how we run VIT on larger images. And actually we are just using a very simple method here. So for example, like for a regular VIT, you just input the 224 image into the model and get a feature map. And if you want to run this VIT on a larger image, what we do is we first get the larger image by interpolating the smaller image. And then we split up this large image into 4 regular size of splits. So there will be like 4 224 by 224 splits here. And then we just send these 4 splits into the model independently. And we will get 4 like feature maps for each split. And then we merge these 4 feature maps into the large feature map, which corresponds to the large image here. And then to get a final multi-scale feature, we will do a very simple average pooling on this larger feature map to get a regular size of feature map. And this feature map should contain some detailed information of the large image. And this feature map is just a regular low-res feature map. And then we concat these 2 feature maps on the channel dimension. And then we have a like final feature map here. And even with this like simple method, you can see that in this pipeline, there's no additional parameters. You can just take any pre-trained vision model and do this thing. It's like training free. And even with this simple pipeline, we already see that larger images can like using larger images can give you better performance than larger models on lots of downstream tasks. So that's basically the first finding in our paper. Is there any question?
So I got one question actually I posted in chat.
Oh, right.
It seems to be if you purposely scale up the image, then you will have more tokens. Then
yes.
even you have the same model with same parameter set, because the sequence of tokens is longer, so there will be more compute in the self-attention process. Is that because of the more compute that give you better performance and therefore will give you bigger model capacity? Is that the reason?
Yeah, that's a good point. So here, when we are designing this pipeline, we are carefully making sure that the final output has the same number of tokens as the regular output. So you can see that even we are using larger image here, and we had a larger feature map. We are doing this pooling to make the feature map to make the feature map as the regular size. And then we concat these 2 feature maps on the channel dimension. So the final feature map will have the same number of tokens as like a regular feature map, only the channel dimension will be larger. And for downstream tasks, like if you're inputting this feature map to an LLM, the number of tokens or the context length will be the same. And since each token will be projected to the embedded space of the LLM input, so the dimension will eventually be the same for LLM. So there will be no like computation overhead on the LLM side. So I'm not sure if that's what you are referring to.
So I guess this green color model here means the VIT, right?
Yes, that's right.
Yeah, but I mean, so you have a lot more of internal compute
Mm-hmm.
compare with a regular VIT on the smaller image. So
Mm.
what I'm asking is, do you think the performance improvement come from
Mm-hmm.
this additional compute by
Mm-hmm.
the color VIT here?
Well, if you so first if you compare with using larger models, um, like the using larger models will make will uh give you like more compute, and using larger image will also cost more compute. And we are comparing these two curves under the same amount of compute. So that's one. Yeah. So that's how we're comparing these two scaling methods. And I think if you want to ask like if the better performance comes from more compute, uh, I would say yes. And I think it's the matter of how you use the additional compute, whether you want to invest that in larger model size, like in more parameters, or if you want to invest that compute in like more image scales or like more detailed information of the image. So I think eventually you need more compute to get better performance. So there's no free lunch here, but the question is how you use that compute. Yeah,
Great, thanks.
Okay, I
yeah.
find the three Q&A in the chat box. So the first
Oh,
question is, do you find the model with scaled up images or the images are scaled only during the inference?
right. Yeah, that's a good question. So we are for all these um so for all these evaluation, we are not tuning the vision model. So we are freezing the vision model. And with this pipeline, the vision model here is frozen. We are just using this pipeline to get a multi-scale feature and send it to a downstream model. For example, if it's for image classification, it will be a linear head. And if it's a multimodal LLM, it will be sent to a LLM. So in all these evaluations, the vision model is frozen. The only thing we are fine-tuning is the downstream model. So it's either like linear head or LLM or whatever. So if that, yeah, yeah.
Okay. The second question is, did you try images taken by cameras with higher
Mm.
resolution instead of interpolating?
Yeah. That's a good point too. So, if you are using the original high-res image instead of interpolating from the low-res image, it will definitely get better result because interpolation here doesn't introduce any additional high-res information here. So that's right. So for practice, if you want best result, you should use the original high-res image. But why the reason that we are doing interpolation here is that we just want to do a fair comparison with using larger models, because when you are using larger models, you don't have those additional high-res information.
Yeah,
So that will be a fair comparison. Yeah,
yeah,
but for practice, you should use high-res image.
yeah. Maybe a lot of concern is that if you taking the image by your camera, maybe there exists a domain gap, so maybe it maybe hurt the performance. Yeah, right.
Uh, well, I well, I don't think that will be an issue because I mean there will probably be some domain gap. So one thing that we did to prevent the domain gap is we split this larger image into the regular size. So because there's another very simple way to do this is you just run this VIT on the larger image, and you can just like do interpolation on your position embedding so that your model can take in larger image. But that will give you some domain gap because like the precision embedding, the interpolation of precision embedding will cause you some domain gap here because it's the model you didn't do this during pre-training. So that's why we are doing the splitting thing. And if you ask, okay, if the splitted image also has some domain gap compared to the training image, I will say there'll probably be some. So I think the answer to that is it will be better if you pre-train on these pre-train with this like larger image scales too, which I will show later that it will give you an even better performance. Yeah.
Okay. Another question from audience is that, but inflation doesn't add any new information to the images. So any intuition why there is an improvement in performance of the model?
Yeah. So I think yeah, that's a very good question. So I've also thought about that myself. So I think the main reason here is because of the multi-skill features. So even though you are not introducing any high-res information when you're doing the interpolation, but your VIT is is extracting the features on a different scale. For example, if it's processing this image, some details, for example, the details of the plants will not be very recognizable by the model. But if you running this model on a crop of the larger image, for example, or on a split of the image, the scale of this feature or the scale of these objects will be different. And that will make the model to extract those features. So you can think of this as like by zooming in the image, you are making the scale of these objects to be the same as in training. For example, in training, you've only seen this large of an object, and if during test time the object is smaller, your model probably cannot recognize it. But if you zoom in, you will drag you will take that object back to the same scale you've seen during training. And in that case, the model can extract the same feature as in training, and that will be better. So I'm not sure if that answers your question.
Yeah. Hi, Baifeng, I have a question. Yeah. Here, did you compare your method with just increase the data scale? For example, if you here use about 100 image and use your method, so you just resize and then split. So have we compare this result with just use about 500 to 212 times 212 image training?
Sorry, could you say that again? You mean using even larger scales or?
You using more images, more
More
224 times 224 images. For example,
Oh, you mean
if you here use just the 100 image, and then you just use the interpolate it, then split, and here you got 5 to 24.
Yes, that's right.
Yeah. So how about compare? How about just directly use about 500 images?
I see. You mean just directly running this VIT on this large image? Is that what you're saying?
No. Just here you use one image and then.
Oh, I see. So no.
How about use 5
no,
images?
Like no the upper branch.
Yeah.
So only the lower branch. No.
But you increase the number of image and keep
increase.
the same. Yeah. Because because here you have 5 times 224 times 224, right?
Yes, that's right. Yeah.
How about just use 5 224 times 224 original images?
Oh, so in that case, those 5 images will be the same?
Not same, just 5 different. Maybe here, maybe it's also a comparison.
Well, I guess if you're evaluating on, for example, if you ask a question about this image, so So what you mean is like you are using 5 images, but these 5 images, they are like different images, like for example, some like irrelevant images. Is that what you mean?
Yeah, right. Do this that I want to evaluate
I see.
the effect of increase the image size and increase the scale. Yeah.
I see. I think for training, that will bring you like 5x more data.
Yeah, right.
I see. So basically, you want to compare between scaling on image scales and scaling on data
scale.
size.
Yeah, right.
Yeah. In this paper, we are not touching the number of training data.
Okay.
And we are not. And actually, the model is pre-trained, so we are not even touching any pre-training stuff. Although we touch a little bit I will show that later. But here, we didn't change the training data. So I think for probably for like scaling on image scales and scaling on data size, there will be some balance here. Like, but it depends on like your budget for your pre-training.
Okay.
So it will be similar as the scaling laws. So yeah.
Okay.
But yeah, we didn't do this comparison or like the tabulations in the paper. Yeah.
Yeah. Okay. Thank you. Yeah.
Yeah. No problem. Okay. Thanks for the question. So yeah. So basically, that's basically the first finding in our paper. And it seems like a very nice story, right? Like using larger image is better than larger model size. But actually, during like when we are doing experiments, we actually found that larger models actually still have lots of advantages. So this is one example here. So this is the classic image classification, and we are comparing the failure cases of using larger models or using larger images. And we find that larger models is actually pretty robust to some out of distribution samples. For example, here the category is television. And for the first two samples, both models, the larger model and the larger image size, both models give the correct answers for these samples. But for the third image, we can see that it's television, but it's with a different texture. So the larger model still can give a correct answer for this, but using larger image didn't help on this sample. And similarly, for this flute category, the easy samples will be some person playing the flute, and both models can do really well on these samples. But for outlier, which is like a statue of some person playing flute, the larger model can still give the right answer, but using larger image didn't help. So it seems that there are still some cases that larger models do really well, but larger images won't really help you. So that brings a question, which is, okay, is there any fundamental advantage of larger models? For example, is there anything that larger models can learn, but using larger image cannot learn? If that is true, then it means that we still need larger models because we need to learn these robust representations. So that's like I think that's a key question of like whether we need larger models or we just need larger images. And we want to figure out, okay, why larger models have this kind of advantage. And to figure out, okay, so if the larger models can learn something that smaller models cannot learn, we are doing a very simple experiment. So this is what we're doing. So basically, we want to compare the representation of larger model and smaller model with larger images. So basically, for example, we have a 256 by 256 image, and we can use a larger version of the image and using the VIT base to get some feature. And we can also use the single scale, but using a larger model to get another feature. And we want to compare these two features. So if these features are similar, this means that smaller models with larger image can actually learn like similar representation as larger models. But if there is some information in this representation that is not contained in this representation, then this means that larger model can probably learn something that smaller models cannot learn, even with larger images. So to compare these two representations, we do a reconstruction based method. So basically, we train a linear layer to reconstruct the feature from the larger model from the feature from the smaller model, but with larger image size. And if the reconstruction is perfect, for example, if our reconstruction loss is 0, then this means that the smaller model can learn the same feature as larger models. But if it's not, then there's probably some problem here. And interestingly, in our experiments, we actually found out that the reconstruction loss is usually far from 0. So it's actually pretty large. So that it seems like there is some information in the larger model that cannot be learned by a smaller model. But actually, if you think about it, this evaluation is probably not the right, it's probably not entirely correct, because there are probably some part of the feature in the larger model that cannot be learned fundamentally, because some feature it's probably learned by, for example, random initialization of the model, or some random dynamics during training. So those features, they are probably not learnable by their nature. So to find out, okay, if the reason for this high reconstruction loss is because of some of the feature they are not learnable by any model, or if it's just because the smaller model cannot learn some feature that larger model learn, we are introducing another baseline, which is we are using an even larger model to reconstruct the feature of this large model. And the assumption here is that a larger model should learn whatever a smaller model can learn. For example, VIT giant should be able to learn whatever representation that the VIT large can learn. And so and then this reconstruction loss will be an upper bound of this reconstruction. So and then we can simply calculate the ratio between this reconstruction portion. For example, if this reconstruction is 100% and this reconstruction is like 80%, then we can get a reconstruction rate, which tells us that a smaller model can only reconstruct 80% of representation that's reconstructible. And that brings us some very interesting observations. So basically, we try this on different types of pre-trained models. So we tried VITs pre-trained on ImageNet, and we tried MAE, and we tried OpenClip. And then we are using either the smaller model, or either the larger model or a smaller model with larger images to reconstruct this VIT large feature. And then, so here this information ratio represents how much representation we can reconstruct. And we can see that for different types of models, the reconstruction ratio is actually very close to 100%. So for example, this is 98, and this is 100.3. So I guess it's a little bit over 100, probably because of some noise. And this one is 99.9. So this means that for lots of different VITs, a smaller model can actually learn a very large portion of the information in your larger model. So that's actually a bit surprising, because you will think that smaller model will definitely have like smaller capacity than larger model. But actually we see that smaller model with a larger image can learn basically this very similar representation as larger models. And there are some other observations here. So for example, we observed that these models, they reconstruct really well on training set, but on test set, they are not reconstructed really well. So I guess there's probably some there are probably some reason to it, which I will show it later. And of course, there is some failure case here. For example, for OpenClef, if we reconstruct a huge model using the base model, the reconstruction ratio is not close to 100%, but it is still higher than using just a small model without large images. So basically, the conclusion is that smaller models with larger images can actually learn very similar representation as your larger model. So this means that these two have probably the similar capacity. And then back to this failure case. Okay, so now we know that smaller models with larger image should learn very similar representation as larger models. Then why are we seeing this advantage of larger models, right? Why is larger model is good at these samples, but smaller models are not? And our hypothesis is that it's because that those smaller models, although we are running those models on larger image when we are doing the downstream tasks, but these models, they are not pre-trained on those larger images. And that will, so the model has not seen any larger image during pre-training. So it probably lost some capability of extracting those representations from the larger images. And to validate this hypothesis, we have some preliminary results on whether like what will happen if we pre-train these models on larger images too. So this is comparison on image classification, and we see that okay, so this one is smaller model, the baseline, and this one is VIT larger model. And if we directly take VIT base, but pre-train on smaller image, and then we directly run it on larger image during the linear probing, we can see that the accuracy is larger than the base model, but is still lagging behind the VIT large. But if we find that if we pre-train this base model on larger images too, then the accuracy is actually larger than the VIT large. And we can see that we get this improvement over the model that pre-trained without larger images. And so that means that pre-training these models on larger image should like improve your model even further. And that's our second finding in the paper. Is there any question?
I find a question in the QA bot. Why
Yeah.
it accepted the representation from different models to be closer? As the model parameters are different, the representations can be different.
Yeah, so that's why we are using, so that's why for the reconstruction, we are training a linear layer to reconstruct the feature. So basically, okay, even the same model can learn different features because, like, for example, if you exchange two channels, it won't affect your representation, but they will be different. So we are learning this small module, which is a linear layer, to do the reconstruction. Yeah. Okay. Yeah, so I'll continue. So basically, yeah, so basically from the previous results, it seems that larger image match a lot for pre-training. And even without pre-training on larger image, you can get pretty good results. And it will it will be better if you pre-train your model on large image too. So this brings up the question of, okay, so what's the next step of scaling up pre-training? Should we just scale it up to very, very large images? Because currently there are lots of efforts on scaling up the model size. So we've seen like VIT22B, which is probably the largest vision model currently. But actually we didn't see like very like fundamental or very essential improvements from those models. Then we want to ask, okay, should we still take on the dimension of model size, or should we try like using larger images? So my answer is that we should definitely try larger image, because we, at least the current vision models, they are not like, they are far from human capability on perceiving this detailed information. Because like if we are like now currently we already have like language models that like even have this superhuman capability on lots of different tasks. But for vision models, we are actually not seeing that. And one reason is that the current vision models, they are not they're like the resolution or the capability of extracting detailed information is really lagging behind human vision. So for example, so this is one table from a benchmark that evaluates the model capability of extracting detailed information, and we can see that for the like these state-of-the-art vision like vision LLMs, they can only perceive up to like 1K by 1K resolution. But if you look at human vision, it can actually perceive a lot more pixels. Like it's probably like 24K by 24K resolution. And this urges us to scale up our pre-training to high resolution, not only because it can approach the capability of human vision, but it's also because that we already seen like lots of improvements on using larger images. But the question is, okay, how should we scale up to high resolution? Right? So what like one vanilla way is, okay, why don't we just like input larger and larger image into VIT? And of course that won't work, because VIT is like very, very expensive on larger image. So like if you want to get the same resolution of human eyes, which is 24K by 24K, and if you do a simple like if you do some math, you will see that by processing one image, it's already consuming the energy of like 100K people. So it's like it's a very, very, very expensive, and definitely you won't want to do that. Then the question is, okay, how should we scale up the pre-training to very high resolution, but in the meantime, preserving the efficiency? And if we go back to human eyes, we can see that our human eyes is actually very good at compressing the information. So the reason that human eyes can perceive very high resolution, but maintaining very low energy consumption, the reason is that we are compressing lots of information of the surrounding world. So if you look at the like how much information is streaming into the retina compared to how much information is streaming into the like the higher hierarchy in your brain, you can actually see that the compression rate is actually pretty huge. Like we are actually compressing like more than 1 million times of the information. So this means that if we want to perceive high resolution but also maintaining efficiency, we need some kind of compression method in our model. And I think one way, like one very promising way of information compression is using the attention mechanism. Because if you look at human eyes, we are not processing all the information, like all the details in the image every second. We are only selecting a very few portion of the image signal. And how we select the information is usually based on two things. So one thing is the image itself. So basically our human eyes can decide which regions in the image is important and which are not. For example, I can see that this screen is probably very important, but the wall is not important because the wall is like a pure color. It doesn't contain much information. So that is what we call bottom-up attention, which means that your attention is depending on the input image. And there is another attention mechanism, which is top-down attention. So which means that your attention does not only depend on the image itself, but it also depends on your high-level task or your high-level goal. For example, okay, I have lots of objects on my table right now. But if I want to like have some water, my attention will be on the water bottle because that's what I want to do now. And I won't look at the keyboard or the screen, even if they are like equally important. So your attention should also depend on your high level task or your high level goal. And that's what we call top-down attention. And with these two attention mechanisms, we can actually compress the information a lot because we don't need to perceive all the regions in the image. For example, with top-down attention, if you're currently if you're answering a question, like for example, is the husky looking at the camera? Then even though there are lots of information in the image, like the cat, the dog, and the pillow, and all those stuff, you don't need to look at all those information. You can only focus on the region that you care about. And in that way, you can actually throw away lots of information you don't need. And that will give you very high efficiency. And in the meantime, you can actually process very high resolution or lots of information in this specific region. So I think for the next step of scaling up very pre-training, I think direction should be using like larger and larger images. So currently our vision models, the pre-trained vision models can see up to 500 by 500 images. So that's Dino V2. And SAM can actually see 1K by 1K, but the representation from SAM is not very like general purpose. So I think the future direction should be scaling on the image scales. And that means we should not, it's not only 500, but probably 1K, 2K, 4K, or even higher. But the question is how we scale, right? And then we definitely need some smart way of scaling. So we don't want to just like violently scale up very large image. We need some smart ways to select the input, select the information. Like we need some way to do information compression while you are scaling up to larger images. So basically, we want to start from scaling on image scales, but we also want some scale selective approach of scaling. And I think that's a very promising direction for for scaling up vision pre-training in the future. Yeah. Is there any question?
Okay, everyone can ask a question in the chat bot, or you want to directly talk with Baifeng, I will allow you to talk. You just, yeah. So maybe I have a question. Yeah.
Yeah.
You want to use the attention and to select some region of the image and then just resize it to maybe to 224 times 224. Yeah, so that you can increase the image resolution with a very large scale, right?
Yeah.
Okay. So what information can we learn from such operation? Maybe
Well,
you can know very high frequency information.
yeah. So basically very high frequency or highly detailed information. And honestly, I don't think there are lots of tasks like so there are definitely some tasks that where you don't need high-res information. Because actually on lots of benchmarks for example, in multimodal LLMs, we actually found out that those benchmarks, they are not very sensitive to your resolution. So probably like 500 by 500 resolution is already enough for those benchmarks. But I think there are lots of other tasks or lots of scenarios where you need high-res information. So one example will be reading text, right? For example, like lots of people already found out that on text VQA or doc VQA, these kind of benchmarks, which you need to read the text, the resolution matters a lot. But the thing is that even on these benchmarks, the performance somehow saturates when your resolution is around 1K, for example. But
Yeah.
that's I don't think that means that you only need 1K resolution. I think the benchmark is not good enough. For example, what if you are not reading only like one word from the image, but you are reading the whole PDF? Then the text will be even smaller. And in that case, it will need even larger resolution. And and that's one example. And there are lots of other scenarios. For example, autonomous driving, you need to recognize objects like that is like hundreds of meters away. And if you're using like 294 by 294 pixel images, that object is only 1 pixel in your image. So that's definitely not impossible to recognize that object. So you will at least need like 1K or 2K resolution for those scenarios. And of course, there are lots of other cases like gaming or medical or lots of everyday tasks. So I think what information you need definitely depends on what task you are doing. I do think lots of tasks need high resolution here.
Yeah. Another question is that can this operation only work on transformer-based network? Because the transformer network has the attention with the different patches.
Well,
Can this
so
work on CNN-based or other?
yeah. So first of all, it can definitely work on CNN. Actually, we had some experiments on convex in our paper.
Yeah.
So the method should be applicable to any vision model. So that's the first point. And I think currently people are prefer to use convex to extract high-res information than using VIT. For example, I think there are some works like Mini Gemini or other papers. So they have two stream of vision signal, a vision feature. So one is using cyclip, for example, on a low res image, and another stream is using a convex on a high res image, for example, 1K by 1K image. And the reason they are doing that is convex is by nature very friendly to high res images because it doesn't have, for example, it doesn't have position embedding, so you don't need to change the parameters when you're processing high-res images. And the computation efficiency is also better because VIT is like it's quadratic complexity, right? But I think that even convex is fundamentally limited when you're using even higher resolution because when you are doing 4K and 4K, although convex they are not like quadratic complexity, it's still very expensive. And I do think in that case, whether you're using CNN or VIT, you need some kind of selection mechanism, for example, attention, to tell the model which region to look at and which region not to look at. And in that case, I think VIT actually is more flexible because for convex, you cannot just randomly, you cannot just drop some of the patches or some of the regions in the image, right? Because the convolution is like it's paralleled for different regions.
Yeah,
And
yeah.
if some
Right.
region is dropped, you cannot save any computation. So I think in that case, VIT is actually better.
Yeah.
So yeah, that's my thought. So I'm not sure which one will win in it eventually, but well, I think either one will need. We should try to scale them up to high res, and yeah.
Yeah, yeah. I have, yeah. You also have solved my question. Yeah. Is there any question? Maybe you can wait more than 1 minute. Yeah. And if no question, we'll yeah, end this talk.
Yeah, sorry. Feel free to email me or like any way of connection. Like we can talk later.
Okay, okay, okay.
Yeah.
Yeah. Okay. It seems like no question from our audience. So let's thanks again for Baifeng's great talk. Yeah, yeah. I believe we
Thank you, Kai.
learned a lot from this talk. Yeah, yeah.
Yeah, thank you for inviting me.
Okay, okay, okay.
Yeah.
Thanks. Yeah.
I hope I will have some chance to visit Singapore in the future.
Yeah, yeah, yeah.
If that's possible.
Yeah, you are always welcome, I think. Yeah. Okay. Okay.
Okay, cool.
Cool, cool.
Thank you.
Bye.
Thanks
Bye.
everyone for coming. Okay.
Bye bye.